Thanks for the introduction. And hello, my name is Lukas. And I will present KernelSnitch, side channel attacks on kernel data structures. It was also a collaboration with Jonas. And so, what is KernelSnitch about? KernelSnitch is a novel operating system side channel which exploits the timing differences when accessing kernel data structures. In our work, we also presented information leakage amplifications to make the timing differences exploitable from user space as isolated and untrusted users. We presented 3 attacks. The first is a cover channel with up to 580 kilobits per second. The second is a website fingerprinting attack with an F1 score of 89.3%. And the third attack is a kernel heap pointer leak in under 65 seconds. Crucially, for the last attack, we are the first of leaking kernel heap pointers using a side channel. And we provide the fundamentals of KernelSnitch open source at this GitHub repository. Let's start with some motivation. A typical system mostly consists of a hardware level and an application level. On a hardware level, there are different entities, for instance, the CPU, the RAM, and the disk. And we all know these entities are susceptible to side channels. Similarly, on an application level, we have, for example, cryptographic algorithms, we have compression algorithms, and other stuff, which may also introduce side channel leakage. So let's assume a dream world where both sides, the hardware level and application level, are free from side channel leakages. And now that the question arises, are we safe from side channels? Have we solved side channel security? Unfortunately, no, because in a lot of systems, the application runs on an operating system, and research on operating system level is pretty sparse. So what we did as a research group, we analyzed one of the most fundamental entities of an operating system, which is the linked list. We have 3 examples. One is the empty linked list, one linked list with 2 elements, and one linked list with 5 elements. When accessing these linked lists and measuring the timing, we observe that accessing an empty linked list is pretty fast. Accessing a linked list with 2 elements is medium fast, and accessing a linked list with 5 elements is notably slower than the other 2. I guess that's, yeah. The second background information for the work is how the Linux kernel implements hash tables. Why the Linux kernel? Because the Linux kernel is a target system we attack. And we also attacked other data structures, but in this presentation I mostly refer to the hash table because it's the most prominent. It takes different linked lists, calls them hash buckets, and then the Linux kernel also uses a hash function, which takes a key as input and the hash bucket index to refer the specific hash bucket as output. And combining both results into exactly KernelSnitch, which I will present. This slide shows the high-level overview of KernelSnitch. We have 2 user processes and 1 kernel data structure. And let's assume process 1 calls or performs a syscall, which internally accesses a kernel data structure. In our case, the hash bucket is empty. So by measuring the syscall, the access timing will be notably fast. Then we wait for another process, which appends elements within this hash bucket. And afterwards, if the process 1 re-accesses this data structure through the syscall interface, the access will be notably slower compared to the first access. And what KernelSnitch does, it deduces security critical information from that timing difference. Before going into detail what security critical information we deduce, we need some primitives. On the one side, we need access primitives, and on the other side, we need append and remove primitives. Access primitives are syscalls which internally accesses these kernel data structures. One example is to get the time from a POSIX timer. In the first stage, it calculates a hash with a kernel address and a user identifier. In the second stage, it obtains a reference of a hash bucket. And in the third stage, it leaks the timing of the occupancy level of that specific hash bucket through timing. For append and remove primitives, these are syscalls which internally appends or removes elements from these hash buckets. One example is creating a new POSIX timer. Again, in the first step, it calculates the hash. In the next step, it obtains a reference of the hash bucket. And in the last step, it appends one new element to this hash bucket. As this slide shows, these primitives are very generic, and these occur a lot of times in the Linux kernel. Now, I showed that we can distinguish different occupancy level of hash buckets by measuring the timing of these access primitives. What we did, we performed 4,096 randomly accesses of hash buckets. A hash bucket has between 0 and 5 timers. And the histogram shows, by measuring the timing, we can distinctly differ how many elements are within the hash bucket. As an example, 0 timers result in an approximately timing of 178, where 3 timers result in the timing of about 205 clock cycles. Now let's continue with the attacks. First of all, we perform the cover channel. In this attack scenario, we control the sender and the receiver. The sender tries to send the message 0101. It encodes this message in the occupancy level of a hash bucket by either appending or removing elements from this bucket. And what the receiver does, it continuously probes the occupancy level of the hash bucket. If the receiver measures a fast timing, it interprets it as a 0. If the receiver measures a slow timing, it interprets it as a 1, therefore obtaining the secretly transmitted message by the sender. What we did, we varied the time slice, so we started with a time of 1 second per bit, and we reduced it to 1 microsecond per bit. We determined the raw capacity, which is the inverse of the time slice, and the bit error rate. We calculated the true capacity, and for the best hash table, we obtained a true capacity of 580 kilobits per second. The second attack case study was a website fingerprinting attack, which is very similar to the cover channel, except now we only control the spy process. What the browser does, it appends and removes elements from when accessing a website. It does that for all hash buckets. So what our spy process does, it continuously probes all buckets to obtain specific or unique fingerprints of websites. Again, thanks for Jonas for the help on the website fingerprinting attack. We analyzed the top 100 websites, used a convolutional neural network, and obtained an F1 score of 89.3%. As last attack, we leaked a kernel heap pointer. Let's recall to an access primitive syscall. First, it calculates the hash with a kernel address and the user identifier. Second, it obtains a reference of a hash bucket. And third, it leaks the occupancy level through the timing. When analyzing the hash, we know the hash function because we can look it up in the Linux source code. We know the user identifier because it's a syscall where the user identifier is the input from the user space. What we don't know is the kernel address. So our exploitation strategy is to call the access primitive syscall with different user identifiers, but with the same kernel address. And inherently to the functionality of hash functions, the same kernel address, but different user identifiers will result in hash collisions. And we use KernelSnitch to detect these hash collisions. In the next step, in an offline phase, so in an offline brute force phase, we test all possible kernel addresses to match the hash collisions with the previously determined user identifiers. We did an attack on the futex hash table. The futex hash table takes as user identifier and user address, and as kernel address the struct. When considering the struct alignment by the page allocator and slab allocator, we obtain 2 to the power of 35 different kernel addresses. We tested all and obtained the correct struct in less than 65 seconds. What we did, we closed KernelSnitch to the Linux security team. Linus Torvald immediately responded that KSLA is broken for local accesses and said no mitigations. However, Keith Cook immediately afterwards said, no, we leak heap KSLA, not code KSLA, because we leak a kernel heap pointer. So therefore, Keith Cook presented a patch. However, Linus Torvald responded with, what voodoo programming is this? And rejected the patch. So, right now, KernelSnitch is still exploitable to this day, sadly. And with that, I'm at my last slide, the conclusion. What we did, we presented KernelSnitch. KernelSnitch is a timing side channel on data structures in the kernel. It is software-induced and largely hardware-agnostic. We presented information leakage amplifications to make this timing difference exploitable from user space as untrusted and isolated users. And lastly, we showed 3 attacks: the cover channel, the website fingerprinting attack, and the novel kernel heap pointer leak. With that, I'm finished. Thanks for your attention.
Okay. We do have time for 1 or 2 questions. So if there's any question, please come up to the microphone. Yep. There we go.
Danke für die Präsentation. Yujing from Ohio State University. So in the last attack, you talked about you take about 65 seconds, which is pretty impressive. But did you have some estimation of the other time overhead for the other attacks, like how much time you probably need to perform that attack?
Perform the cover channel?
Yeah, for example, like the browser fingerprinting and so on.
If I remember correctly, for the browser fingerprinting, we measured 15 seconds of accessing a website, and we did that for each website 50 times or 100 times. Yeah.
Yeah, that sounds pretty nice.
Okay.
Wonderful work. Thank you so much.
Thank you.
Hi, great talk. This is Tyler from UF. I had a question on the patch that Linus had a problem with. Did it was it something negative about it? Like, was there some kind of slowdown in the system or anything that he didn't like in particular, or just did he not like the variable names? I'm just curious on that part, if you know any more.
Yes, yeah. The core idea of the patch was to introduce a third input. The third input is some randomized value. So a randomized value which is not unknown to the user, so that we can brute force all attacks. And what Keith Cook does, he tried to, if I remember correctly, he tried to swap some other kernel addresses around and use that as the random value. And Linus Torvald said, like, no, you can't do that.
Voodoo.
Yeah.
Thank you.
You're welcome.
Okay, then let's thank Lukas again.